Hey guys, welcome back to Cloud Security Masterclass. Today we are talking about something that's quickly becoming a real challenge for cloud security teams: identifying AI workloads running in your AWS environment. Right now, every company is racing to integrate AI into their applications. Some teams are building directly on Amazon Bedrock, others are bypassing cloud native AI services altogether and calling external models like Anthropic or OpenAI directly through their APIs. And increasingly, teams are moving beyond simple model calls and building AI agents that can use tools, access knowledge bases or RAGs, and make decisions autonomously. And in most organizations, these AI workloads ultimately run inside your cloud environments because that's where the compute, networking, IAM, and managed AI services already exist. Now imagine this. You are a cloud security engineer responsible for protecting your AWS environment. You want to enforce AI security controls. You want to monitor how AI is being used. You want to make sure sensitive data isn't being exposed. But before you can do any of that, let me ask you a simple question. How many AI workloads are actually running in your AWS accounts today? Can you confidently answer that? Because before we can secure AI, we first have to detect it. And that's exactly what this video is about. Now, there are a few reasons why discovering AI workloads is becoming so important. First, shadow AI. Developers can integrate LLMs into cloud applications like Lambda, ECS, EKS without the security team even knowing. If you don't know these workloads are interacting with AI models, they can't be assessed or governed from an AI security risk perspective. Second, data exposure risk. Applications might send customer data, PII, source code, internal documents, or even secrets to external AI models. If you don't know which applications are making these calls, it's extremely difficult to assess or reduce that risk. And third, AI governance. Maybe your organization requires Bedrock guardrails. Maybe prompts must be logged. Maybe every model invocation has to go through an approved AI gateway. Those are all great controls, but they only work if you know where your AI workloads actually are. So in this video, I'll walk through 3 common AI deployment patterns that I built inside AWS. Each one leaves a completely different forensic trail. For each one of these patterns, I'll show you the evidence you can use for detection, which AWS logs to look at, and how to attribute AI activity back to the originating workload. So let's jump into the first demo. So let's start with the first and probably the most common deployment pattern that you will see in AWS today. This is a Lambda function invoking a foundation model through Amazon Bedrock. If you look at the code, you'll see it's a very straightforward Bedrock API call. It sends a prompt to Claude, waits for the response, and returns the generated text. This is representative of how many production applications integrate with Bedrock today. I will invoke the function so we have some activity to analyze. I'm triggering it directly from the Lambda console, but exactly the same detection technique works regardless of whether the invocation comes from an API gateway, event bridge, or some other AWS service. So the Lambda is invoked, and now you can see the response, a simple hello that is returned by the LLM back. Now let's switch over to CloudTrail and see what evidence this AI workload generated. Now you'll see that this is recorded as an invoke model event from bedrock.amazonaws.com. Let's open this event and look at the fields that are most useful for attribution. One of the most valuable fields here is credentials issued to. Notice that CloudTrail records the full Lambda function ARN that generated this model invocation. That means we can directly attribute the AI request back to the workload that made it. From a detection perspective, this is much better than simply knowing that an IAM role called Bedrock. We also have the user agent here. In this case, it tells us the request originated from an AWS Lambda runtime, including the Python runtime version. This becomes useful if you're trying to distinguish developer or runtime or SDK calls. In the resources section, you can also see the LLM model that was invoked, in this case called Haiku. Another interesting field is additional event data. This gives you input token count, output token count, and the inference engine. This can be very useful for inventorying AI usage or estimating model consumption across workloads. So let's summarize what we have learned from this pattern. For workloads using Amazon Bedrock directly, CloudTrail already provides an excellent detection surface. By looking at invoke model events, you can identify AI workloads, attribute them back to the Lambda function that made that call, determine which foundation model was used, and even collect useful metadata like token counts. Native Bedrock workloads and therefore one of the easiest AI deployment patterns for cloud security teams to discover. Now let's take a look at a much more challenging scenario. What if developers completely bypass Amazon Bedrock? In this example, I have a Lambda function that directly invokes Google Gemini using an API key. You can see the API call here, along with the prompt being sent to Gemini. From a security perspective, this creates a visibility gap because the application isn't a native AWS AI service. AWS has no idea that LLM is being called. So let's invoke this Lambda function. The invocation completes successfully. In this case, I didn't receive a response because the API key doesn't have any credits configured, but that's actually okay. The outbound request is still made, which is all we need for detection. So how do we discover this workload? The key is that this Lambda function is attached to a VPC. For workloads running inside a VPC, every outbound connection begins with a DNS resolution. In this VPC, I have enabled Route 53 resolver query logging, which records every DNS lookup made by workloads inside this VPC. Now let's take a look at these resolver logs and see what they tell us. Here, we can clearly see a DNS query being made to generativelanguage.googleapis.com, which is the endpoint used by the Google Gemini API. The DNS log tells us that something inside our VPC attempted to communicate with Google's generative AI service. Now the next question becomes, which workload made that request? If we look more closely, the resolver logs contain the source resource that generated the DNS query. At first glance, this looks like an EC2 instance ID. It's actually not an EC2 instance. Instead, this is an internal AWS hyperplane worker that's responsible for networking on behalf of Lambdas that are connected to VPCs. If I copy this source IP address and search for it in the EC2 network interface and click on the ENI, I could see that this ENI is of type Lambda, and in the description, we could also see the name of the Lambda function. So we can attribute the DNS request back to the Lambda function that initiated it. So to summarize, when applications call external LLM providers like Gemini, OpenAI, or Anthropic directly, CloudTrail no longer provides visibility into model invocations. However, if those workloads are inside a VPC, Route 53 resolver query logging becomes an excellent detection surface. Finally, our third use case is around AI agents. Instead of an application simply sending a prompt to LLM, we now have an autonomous agent that can reason, decide when to use tools, and take actions on behalf of a user. I've already built an agent using Bedrock AgentCore Runtime service. We're still using Lambda, but Lambda is no longer responsible for invoking the model. Instead, Lambda is now a tool that the AI agent can call. As you can see in the Lambda code, it simply acts as a shoe inventory system. It returns the available inventory for different shoe models and sizes. The actual workload invoking the LLM is now the AgentCore runtime. The agent itself is packaged as a container and stored in Amazon ECR. Inside the agent code, you can see the system prompt that defines the agent's behavior as a helpful shoe store assistant. And you can see that Lambda is registered as one of the available tools that agent can use. So let's test the agent. I will invoke the agent directly from the AgentCore console and ask, do you have Nike Air Max in size 10? Behind the scenes, the agent decides it needs inventory information, calls the Lambda tool, receives the response, and then generates the final answer using Bedrock. Now let's switch over to CloudTrail and see what evidence this generates. The first thing that caught my attention is this. For this single user prompt, CloudTrail doesn't show one model invocation. It shows 4 converse stream events. The reason is that an AI agent isn't simply forwarding your prompt to an LLM. It's orchestrating a workflow. The event source is still bedrock.amazonaws.com, And notice that all four of these events are attributed to the same AgentCore username. Another thing to notice here is the IAM execution role that I assigned to the runtime. This is exactly what we want to see. In a production environment, these model invocations should come from a short-lived IAM role, not an IAM user, and certainly not the root account. Another interesting detail is the user agent field. Besides telling us that this came from AgentCore Runtime, it also reveals which agent framework is being used. In this case, it's Strands agents. If your organization uses LangGraph or Crew AI, this becomes a useful way to inventory different agent frameworks running across your AWS environment. But here's where I ran into something interesting. So far, we know the agent executed, which IAM role called Bedrock, and even which agent framework was used. But who actually invoked this agent? Was it a developer, an internal application, another AI agent? If I search CloudTrail for invoke agent runtime, there is nothing. From a security perspective, this is a huge blind spot. To capture that missing identity, I created a dedicated CloudTrail with data events enabled for Bedrock AgentCore Runtime service. And now, after I did another test invocation of the agent from the Bedrock AgentCore console, and I go to the CloudWatch logs where the output of the trail is being stored, I can see a log entry for the invoke agent runtime event. Notice here the user identity field. This records who actually invoked the agent. In our case, this is the root user, which is a big security issue if you see this in a production setup. This is the only event that captures the external caller for the agent. Without this event, you know the agent ran, but you don't know who started it. There's one more field that's incredibly important. This is the runtime session ID. Think of this as the correlation ID for the entire agent execution. The same identifier appears in every downstream Bedrock event generated during the interaction. That means you can now connect the parent agent invocation with every model invocation and build the complete execution chain from end to end. Across these three demos, we have now seen three completely different ways that organizations are building AI applications on AWS. And more importantly, we have seen that each one leaves behind a completely different forensic trail. As AI adoption continues to accelerate, one of the first responsibilities of cloud security teams is not deploying guardrails. It's building an accurate inventory of AI workloads. Because before you can govern or secure AI, you first need to know where AI is running. Thanks for watching, and please subscribe for more AI and cloud security demos.